This video contains the solutions for 18 through 21 on your practice AP Physics C test number 2, practice number 2. Simple pendulum has a period of 2 seconds for small amplitude oscillations. That puts me in mind of the equation T is equal to 2 pi times the square root of L over G. That's how you find the period of a simple pendulum. Length of the pendulum is most nearly, let's see, the period is 2 is equal to 2 pi times the square root of L over about 10 or 9.8-ish, whatever that is. So let's see, those would cancel out. So 1 over pi is equal to the square root of L over 10. And that's about 1/3, and the square root of 1/9, or 1/9 would be 1/3. So I think L is going to be close to 1. You'd have to do a little approximating there, I guess, but the 1 works best, right? Because the square root of 1/10, well, 1/9 would be 1/3, and pi is pretty close. 1 over pi is close to 1/3 too. Number 19. Which of the following equations could represent the angle theta that the pendulum makes with the vertical as a function of time t? Well, this is simple harmonic motion. So the angle theta, that's like our displacement, right? Remember the so-called small angle approximation, that for small angles theta is approximately equal to the displacement x. So basically we're doing like our the x equation for simple harmonic motion, so our position equation. So that's the maximum theta, that's like amplitude, right? That's like the same thing. And then they're using the sine function, and that would be omega t. Now what's omega? Omega is, remember, just for from pre-calculus, omega is 2 pi divided by period. So that's, what is the period? The period's 2, so that'd be, omega would be 2 pi over 2, right? Because they told us the period's 2. So omega is pi. It looks like this one, right? That has pi right there. Oh, that's B. Oh, the Atwood's machine. If you remember, what's the acceleration of the Atwood's machine? There are tensions T and T. There are free body diagrams. The net force on the big block is equal to mg minus t, and the net force, and that's let's see, net force is equal to mass times acceleration. So that gives us that equation. And for the smaller one, since it's going up, we get its mass times acceleration is, this is the greater here, so t minus mg. And getting rid of the t's, setting one equal to the other, doing some substitution, you should arrive at an answer of E. I'll leave that simple algebra for you to complete. You could also think if the two masses were the same, it would not accelerate, right? It would be balanced out. So I think we would want the acceleration there to be 0. That points us toward something with that difference. And we know from our lab way back when it does depend on both masses. So maybe you can remember that, but it's easy enough to get it. Number 21, for a particular nonlinear spring, the relationship nonlinear spring, that means it does not follow F equals kx or F equals negative kx. It's got some other relationship, which they're giving us here. Is given by this equation. What is the amount of work done by stretching the spring a distance x sub 0? Well, remember, work is equal to force times distance. But if it's a variable force, then you have to do the integral force times distance, or the area under the force curve if you have it as a function of x, and we do. So work is equal to, let's see, from 0 to x sub 0. We're going to stretch it from equilibrium to x sub 0, and that's kx squared dx. So antiderivative of that would be k over 3x cubed from 0 to x sub 0, and that is equal to e.